Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome people of the future. We are going to continue today with an actual lecture with actual material, because last week was just a small appetizer to get us started. And we are going to start with something that's called Boolean retrieval. So, you know, whenever you query data, in fact, I hope you will realize by the end of the course that this is a database course. But it's a database course on the specific case of unstructured data. So it's not going to be relational tables with SQL. I mean, we'll see some of them, but unstructured data. But whatever the shape of your data is, you still have the same sorts of paradigms in databases. You have query languages, you have a logical model, a data model, you have syntax, you have, what else do you have? You have optimizations like indices and so on. And in fact, as you will see, we have all of that in information retrieval as well. So in fact, unstructured data is just like tables or cubes or trees of graphs. It's just another database topic. But in our case, the query language that we will use will be a simple language that is Boolean based with and or not. And we will build today actually an entire system that is able to run queries on a large collection. And you will even have in the exercises some programming assignments, will be next week. So this week is just a Python tutorial, but next week you will have as a programming assignment to build a system like that. Not from scratch, the TA team was kind enough to provide you with templates to start with. You will already have the context-free grammar set because this is not a compiler's class, but you will have to write the rest of the codes to make it all work. So I told you the data shapes. I know I'm repeating myself, but this is probably the one most important message that I have in all the courses that I teach, is that the data shape is super, 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 super important. I cannot emphasize it enough. There are tables, there are trees, there are graphs, there are cubes, there is unstructured data. If you get that wrong, if you do not take a step back when you query data, take a step back, look at your data and ask yourself, is it a table, a cube, a tree, a graph, or unstructured? You are going to potentially get a slower system than you could. It's going to be super slow. And it also lowers your productivity because you're using a screwdriver with nails, basically. So this is really super important that you get that right, because the shape determines everything. It determines the query language, the storage, the kind of storage you use, and so on. That makes a huge difference. In this lecture, yeah, I'm sorry, I don't manage to get rid of that thing with Sophos. I pretty much tried everything I could to make that pop-up go away. All right, hopefully it doesn't come back in the lecture. So yes, we are focusing on this lecture on unstructured data. And the overall way of formulating the problem that we are solving in the case of unstructured data is that we have an information need. So the notion of information need is a bit abstract. This is whatever you're looking for. Basically, that would be a statement in English of what you're looking for, but it's not exactly that. In fact, it's more what's in your brain that you are expecting. So it's a little bit abstract, but in the end, you have an information need. You're looking for something, and you have large collections, books, libraries, so the Library of Alexandria or of Congress, the British Library, and you want to find unstructured data. Right, and I'll come back later to the difference between information need and query. For now, we'll just directly work with the query, assuming that the query matches the information need, because this is then more technical and formal. But I'll just try to convince you that it's not that trivial to find the right query for what you are looking for. Why don't we start with a question that I have for you on the Clicker app. So this is the address right here that you can use if you haven't seen that before, or you can install the app. It's an ETH app on your smartphone. I notice with time, every year that passes, that the number of laptops in the lecture hall is decreasing. I mean, when I was a student, everybody had a laptop. So the room was full of laptops on every table, and now everybody has smartphones. So you see the evolution of technology. All right. So can anybody tell me what the Dewey decimal classification is? Is it the core algorithm used by Google to index the web? Is it a number-based system used by many libraries in the world to sort and retrieve their books? Is it a standard used by mathematicians to classify sets, N, Z, D, Q, or C? This classification is also paramount to information retrieval, as documents are encoded as numbers. Or, yeah, query D-way and decimal 5 classification, curl, X posts. Yeah. That's kind of a Boolean query, by the way. It's not fully, but this end and the keywords and so on is kind of what we are going to do today, the fourth answer. Right, let me give you some time to connect and so on. Works both from the lecture hall and from Zoom. All right, let's look at your answers. So indeed, it's what libraries all across the world are actually using, or actually were using, I think they still are today. In order to find books, you are looking up this table of codes, and depending on the field that you're looking for, and then it's funny times because sadly you cannot do it at ETH. But basically, if you have a large libraries, you just find the code you're looking for, go to the place, to the actual shelves, and then all the books are together of the same category. And you can really take the time to go book by book, and that itself is a wonderful experience. At ETH, we have robots. So this is all hidden in the background, and then the little robots are bringing the books to the desk. And then you have the luxury of directly getting the book out. Of course, it removes the experience of actually seeing all the books in the shelves, but it's nevertheless quite practical. So yes, you are absolutely correct about this. I can return to where we were. And here too, if I prepared everything correctly, we should land exactly where we were. So let's then try now to start building a system. So imagine you have a collection of documents. I'm going to simplify by assuming that you have the luxury of having them as text files on your laptop. Of course, if it's in actual books, that's more complicated, but let's assume you have plenty of text files sitting on your laptop and you're looking for something. Well, something that might come to mind, especially to computer scientists, is to use grep, right? Who knows grep? Right. So it's based on regular expressions, the ones you learn in theoretical computer science. It's a simpler form than context-free grammars that look like this, with this vertical bar for or. You have the clean star for one or more. You have the plus for one or more. Then this square brackets means any letter between A and Z, and so on and so on, right? So if you have a regular expression for what you're looking for, then you can use grep in order to find your information. What's very important is that you could consider that regular expressions form a query language, right? This is a query language. You can type that, use it with grep, and you will get lines. Basically, grep works with lines, right? Let's do it. Oh, let's not do it. Okay, my slides do not agree with me, but so we'll do it. We'll do it in a bit. So the problem of grep is if we want to search a very, very large collection like the web, then that doesn't really scale, right? So you have a problem with grep if it's not all on your laptop, right? So we need to find some different technology for the entire web. And in fact, this is exactly why at the time, this is an excerpt from a book about the early years of Google back in 1998. But the idea back then, which sounded completely crazy, was to download the entire web, to download the entire internet on your servers in the basement, in the garage, and then to index it. And it was, of course, much more difficult than it seems. Took actually years. Nowadays, it's actually simpler. In fact, there are research groups that even now casually talk about downloading the web. This is no longer really something that is undoable. And in fact, any search engine will pretty much scan the entire web in 48 hours, just to give you to contrast that with the years here. So in 48 hours, this is typically the refresh rates that you get. But of course, it's done in parallel with plenty of servers in a data center and so on, not just with a laptop. All right, then you can use proximity search in order to, oh, I know what happened, why it will not show me the grep, because I think I just opened the wrong file. Let me show you the grep. I really want you to see that. I'll come back to the proximity search. I think this is this one. I just did not land at the right place after asking the question. This is what I wanted to show you. So this is a corpus. In that case, it's Sherlock Holmes. So the reason why many people use it is that it became public domain recently. So now you can basically download that and it's totally fine. You can even share it and so on. It's public domain. This is the very beginning. And in fact, it takes 3 megabytes. Everything that Sir Arthur Conan Doyle wrote about Sherlock Holmes fits in 3 megabytes. So it's a text file like this. So now, imagine you're looking for lawyer. You could grep lawyer in that document. And if you grep for lawyer, this is what you will get on the command line. If you try, it will basically find all the lines where that word appears. This is how grep works, right? So for example, it's going to find that line. And then on the command line, it's just going to write down all the lines that contain this word, lawyer, right? You can, of course, tweak on the command line. You can also ask that it displays the context, like the 5 lines above, the 5 lines below, and so on. But basically, in essence, this is what it does, right? So we have a query language like this. We can supply queries, regular expressions. And then the output of that is lines of text that match the query you're looking for. So this is how it works, grep lawyer corpus, and then you will see this is what happens on your screen. So of course, it doesn't make sense to read it because these are really lines all over the place. But if you look closer, you see lawyer, 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 lawyer. You can do it on every line, right? So these are all the lines that contain that word, all right? So this is one way of doing it using grep. Now, because we're interested in Boolean queries, right? So Boolean query means that you might be looking for 2 terms on the same line, right? In the command line, you can actually use pipes, right? You can grep for a word and then pipe it over to another command and then grep for another word. So now we look for lawyer and Penang and we find 2 places, 2 lines in the 3 megabytes that satisfy the query, right? So it actually does the job, right? But of course, it only works locally on your laptop. What about other operators like and not? When you know that, or you might know that grep has this parameter -v here, right here, that inverts the whole thing. So it's going to remove the lines that contain the word silver. So if I go back here, there was silver right there. You don't want it. And there it disappeared because you pipe through a not silver, right? Who is following? Okay, so this is just to tell you that with grep, we can actually do that. It's rudimentary, it works, and it has shortcomings. And these shortcomings is what I told you that you know, it's very challenging to do it over the web because you would have to download it entirely. It's not easy at all. There's also shortcomings with proximity search because sometimes you might be looking for 2 words that are near each other. Right, but you know, this goes beyond what you can do with grep, right? Well, you could argue that if you put the 2 of them on the same line, this is proximity, but what about 1 line and then the line after that, right? So this is where you start seeing that with grep, you're reaching the limits, and that is actually quite limiting the sort of things that you can do. Another problem with grep is that it doesn't rank. Yet, in most of the systems that we have today, especially when you search the web, you get ranked results, right? You get and typically people look at the first 10 and will rarely go to the next pages, but this is ranked. And look at that, there are 72,800 results. If it was just dumping at you these 72,800 results unranked, how can you work with that, right? It doesn't work. So the idea of ranking is to assigning scores to the documents and to display in priority those that have the highest scores that they believe you will be interested in, right? And typically, so if you like, that guy's rusty grabber, but it's going to display Wikipedia or the sort of pages that are quite popular. So that's known as the PageRank algorithm, right? But grep doesn't do that. With grep, you have no way of ranking the results. In fact, today we are not going to look at ranked results either with the Boolean queries. We'll look at ranked results in a few weeks. We'll see that there are ways to do that with linear algebra, but we'll come back to that. Another aspect is that grep is scanning the files, right? It's linear. If you double the number of files or the number of bytes you're looking for, it's going to take twice as much time, right? But in databases, we like to have indices so that it's instant, right? You can have a database with billions of records. And if you do a lookup looking for a specific record, it's going to return in just a few milliseconds. This is the magic of indices. But grep doesn't have that. Grep is just going to do a brute force scan of all of your data, and it's going to take a lot of time. If you try to grep the web, you can really come back in a while to get your results, as opposed to just a few milliseconds as it is done with a search engine. Okay, so what I hope that I convinced you of is that grep has limitations, and that's just not good enough. Who is convinced of that now? Okay, very good. So now we are going to build an actual system that is more robust than that, and that is always starting with a data model. Exactly for database lectures, it's the same. In a relational database lecture, you start with a relational model, right, with rows and columns and so on. If you study XML and JSON, like we do in big data, then you have a tree-based model. If you are studying data warehousing, you have cubes with dimensions. And if you are studying, I don't know what's the last one, graph databases, you have the notions of vertices and edges. All right. So let's start with the data model of unstructured data. That might be surprising to you that there is a model at all, but there is actually one. So what do we have in our model? Just like the equivalent of what would be rows and columns in a relational table. Well, first, we have the notion of documents. A document is a book, for example, or it can be also a DVD or whatever, but typically for this lecture, we'll assume books. Each one of the books right there is one document, right? The term that data modelers like to use is the notion of primary citizen. We say that a document is a primary citizen in our model, right? So in our data model, we have a couple of primary citizens. So the first one is the notion of documents. You see the documents when you query, for example, here is the ETH library or the ETH search. When you have your query results appearing like that, every snippet that you see basically gives you one document. Then you click on it, and that will open the document. So in that case, we have 4 documents. And as I said, in a library, this would correspond to books. But again, it really depends on your use case. And there are places where we'll come back to that next week, that it might not be exactly that. But for today, we will assume a document is a book, right? Next, we have the notion of term. This is the second primary citizen of our model, right? So documents and terms. So a term, you can think of, it's an abstraction, but you can think of that as a word, right? Like each line here is a term. Sherlock, lawyer, Switzerland, Unterwalden, Nidwald, that's the actual name of Nidwald. ETH Zurich, person, watch, run, paper, book. These are all terms. For now, I'm going to keep aside what exactly is a term and where do you put the borders. Like, for example, Unterwalden Nidwald had spaces, so you could not just say the spaces are enough to separate the terms. I'll come back to that next week, right? Also, ETH Zurich is not 2 terms, but just one, technically, if you want to keep them together. But for today, we can assume in the very simple case that we can just tokenize by space and be done with it, right? And then we'll come back next week with a bit of the complexity, saying, okay, it's not that simple in practice, right? But for the purpose of oversimplifying, the document is a book and a token is separated by space. Simplify. All right, and then you can look at a document. Who knows that one? Oh, some of you. Yeah, I could actually sing it. No, I'm not going to do that to you. It's actually something you can sing. So we have und das the Flamme again, and so on and so on. All right, but you don't need to understand Swiss German. That's totally okay if you don't. This is a document. We'll call it D, for example. And now we need to talk about the relationship between a term and a document. There are several ways that you can actually relate terms and documents. First, you have the notion of saying that a term is included in a document. In that case, the term Hölzli is included in this document, in this song. Okay, this is inclusion. This notion, so you really have to think of it in an abstract fashion as modeling. We have a term in a document and a relation of inclusion between a term and a document. As an analogy for what we are doing here, think of geometry. In geometry, you have points, you have lines. A point can be on a line can go through a point, lines can be parallel, and so on, right? So of course, when I talk about points and lines, you probably visualize points and lines in your mind, right? But if you do it in terms of actions and purely mechanical reasoning, you don't need to. You just have the abstract notion of a point, the abstract notion of a line, and the abstract notion of a point being on a line. And in fact, there are people who invert the whole things, but by swapping points and lines, you can actually do this in an inverted fashion, that's saying that a line is a point and a point is a line, right? This is just to tell you this is an abstraction. So we have terms, we have documents, and we have a relation of inclusion between terms and documents, right? Hölzli is included in that document. We can casually express it with set theory with that symbol, but I'll show you it doesn't have to be sets, right? But in that case, let's write it down that way. Hölzli is a member of the document. It belongs to the document. So have the notion of set here. However, you might have noticed that Hölzli appears several times, twice in fact. And that might be relevant to us. Maybe we want to actually take that into account when we query, because if a term appears twice in a document, it's not the same as if it appears just once, right? So we could want to also have in our data model the cardinality, the number of times, the number of occurrences. Occurrence is the word for that. And we write down that the occurrence of Hölzli in our documents is 2, at least on that screen, right? So we have the notion of occurrence. We are counting. This is no longer a set. Do you know the word for that? A set doesn't have the notion of occurrence, right? But what we call it if we extend the set with numbers of occurrences? Yes, I heard it. A bag, exactly. This is called a bag, right? But we could also go further than that and ask for one more thing, which is the order. In that document, when we read, it's linear, right? It makes more sense to read a book from the beginning to the end. And in that case, Flamme comes before Für. In fact, that's the whole storytelling, right? If you follow the story of the song, this is the order in which things go, right? So we might care that a term can occur before another term in a document. I should have added that in document D, right? So we have the order. What is it then? A bag doesn't have that, right? What is it? A list, exactly. So you see, we already have set, bag, list. We start seeing a bit of data structures in there, which is good. I mean, that's data modeling, right? So abstract data types are not really a surprise. So basically, yes, that's a list. And if you consider now that the relationship between the set of documents and the set of terms is in terms of lists, a document is a list of terms. That's now a definition of a document. It's a list of terms. We have inclusion, check. Occurrence, check. It's sensitive to the number of times it appears there. Order, check. A list is ordered, right? Now, what about giving up some of that? Because if we really have the documents as lists of terms, we really need to store it all, right? It takes a lot of space. Maybe we don't really care about the order in which the words occur for the purpose of our search. So let's drop the order. I don't care about the order. So I'm going to get a bag, as you told me, right? This is now a bag. Of course, you cannot really enjoy the story of the song anymore, but you still have the words in there. And you have the number of occurrences, you see? Hölzli is here and here. So this is why it's a bag and not a set, right? Here and here. All right. And you could also argue, by the way, Zünd-Hölzli, that it also belongs to that, at least in the cantons where you call that a Zünd-Hölzli. we'll look into the notion of splitting and having actually separating the terms also next week, right, when we go in there. But today, again, if we just separate by spaces, these are not the same terms. All right, but anyway, now I have a bag. And now what I could do next is to throw away also the occurrence. So I give up on the occurrence and I get a set. Yes. And now I remove the duplicates. This is how I do it. And now this is a set. So what does it mean? I have 3 different ways that I can do things, and all are okay. I could say a document is a list of terms, or I could say a document is a bag of terms, or I could say a document is a set of terms. I just have to make a choice. I have to make up my mind, this or this or this. Right. But today, we are going to take this approach with the set of terms. In other weeks during the semester, when we look into other querying paradigms for information retrieval, we might use bags instead, or we might use lists. Right? And every time I will be very clear, I will tell you this is the list semantics, the bag semantics, the set semantics. More precisely, we say set of words, bag of words, list of words semantics. Okay. Okay, so far so good. Is everybody following? Okay, so bag, list, set, we have a choice. But today, we are going to focus on sets of words. What does it mean? We forget about the order of the words. We forget about the number of occurrences of words in a document, and we only focus on a word being included or not in a document. You might have noticed that now I said word and not term. This is about terminology. In casual language, we tend to say word a lot. I will try to convey the idea and differentiate between this terminology. So in particular, what you need to understand is the notion of token and the notion of term, and I will define them today. Word is more of a casual way of formulating things, and we tend sometimes you use word meaning term, and sometimes you use word meaning token, right? But normally it's clear from the context. If you really want to be precise, then use term or token, and I will define the difference very shortly. All right, now, how do you model a set? So you have documents, set of documents, a set of terms. How do you model that each document is a set of terms? Well, look again at the model. We have the notion of documents terms, contains or not terms. The mathematical name for that is relation, right? For every pair of document and term, it's a 1 or a 0. It's a yes or not. Either the document contains the term or it doesn't. Who sees that this is 2-dimensional? Right? If you would draw it, actually. Okay, very good. So indeed, you could see it as a matrix with rows and columns. So I for the terms and J for the documents, right? And you put a 1 in the matrix if document J contains term I, and you put a 0 if document J does not contain term I, right? And then that gives you the contains IJ. That's a Boolean. So this is what you get. That's called an incidence matrix. And you can see in this incidence matrix, for example, that contains Y5. Where is my hand? Oh, there. Yeah. Oh, I was too low. Contains Y5 is 1. How do you see that? Because 5, this is the document 5. In that column, we have document 5. And we see that document 5 contains terms Y. It also contains term X. It also contains term W. It does not contain term V. It does contain term U, and it does contain term T, right? And you look at each document vertically, and you see the terms that they are in there. Can you reconstruct the original document? No, you can't, because you forgot, we have a set of term semantics, so we forgot the order and the number of occurrences. So we lost information, but we just kept just a notion of inclusion for the purpose of querying, and that's just a design decision. Okay. So now if you look at it mathematically, what is this relation contains? Well, that's just a function that associates every pair term document with a Boolean, right? You can see it as a function from terms and documents to Booleans. Who is used to this power notation for functions? Okay, many of you know it, right? So when you have b to the power of a, it means the set of functions from a to b, right? Very convenient notation. All right, so b to the power of terms and documents. And so if you want to know how many zeros and ones these are, then it's 2 to the power of terms and documents, right? All right, to the multiplication of terms and documents. Okay, question for you? We have is the clock actually moving? I'm going to check because I have the feeling that the clock stopped. Ah no, it's still quarter to 11. Okay, I thought I was in like in these movies where you are in a time loop. All right, so all right. Then to check that it's clear to you, here's an incidence matrix with 10 documents, 1 to 10, and 6 terms, T, U, V, W, X, Y. And I'm asking you what query Y return. Y is the query. I'm looking for Y. What does it return? 1, 2, 3, 4, 6, 7, 9, 5, 8, 10, nothing, the empty set, or everything, all documents. All right? Y. Okay, that was quick. 44 answers already, 45. We still have incoming answers. Right, now it's stabilizing, all right. Let's look at what you said. Well, we have a majority of 5, 8, 10. How do I know that? Well, you can see on the last row at the end, look at the ones on the last row. You will see a 1 below the 5, a 1 below the 8, and a 1 below the 10, right? So I cannot show it for those on Zoom, but in the lecture hall, I can just show it. This is here, 5, 8, and 10, right? And those on Zoom, just look at the last row at the very bottom. You have only 3 ones in column 5, column 8, column 10. Okay, for who is that clear? For whom is that clear? So I forgot the M. Okay. Yeah, you see how grammar is important. If I miss the M, then all right. Now should I go to? I think it's 3. I hope I'm not making the mistake again of landing at the wrong place. But we'll see where we land. Okay, so we did it with Y, let's do it with U, basically just to show you what that means. So for query U, for example, you would look at that row and see that it is in 3, 6, 8, and that's it, right? So 3, 5, 6, 7, 8, right? So these are the results of your query. So you see that with this incidence matrix, we are already in a position that you can take queries and answer queries, right? A query for the moment can be a term, and the output of the query is a subset of the set of documents. It's a set of documents. Okay. Now, how do you resolve a Boolean query? Because Boolean means not and or. So if we say not you, how do you do that? That should be simple, right? I'm assuming this is very simple because we start easy. How do I query for not you? Yes? Maybe the microphone, we can throw the microphone. Oui, sorry? Yes, exactly. We invert the entries. We have a cube microphone here that we have that makes it very easy. We try to use it in the future so that the people on Zoom can hear you. Otherwise, I will just repeat what you are saying. So indeed, you're absolutely correct. We take the entries in U and we invert them. We basically do the logical not, right? So what we get then is documents 1, 2, 4, 9, and 10. This is query U. Okay, now what about end? If we have an end, in that case, U end X, what do I do? Yes, maybe the microphone. Wow, oh, wow, almost, yeah. Yes, a logical AND bitwise between U and X, exactly, right? And do you agree with that? That this is what we get? Yeah, absolutely. So this is a logical AND indeed. So you know how that works, right? You studied logic. So 0, 0 is 0, 1, 0 is 0, 1, 1 gives you 1. So this is the case where we do have here 1, 0, 1, 0, and 1, 1 again gives you a 1 over there. So it's a bitwise logical AND indeed, right? And then we get documents 5 and 8. So you see it's becoming more complex now, the queries with AND. And with OR, it's just the same bitwise logical OR. So you have these two rows, U and X, so it's U or X. I have to be careful when I use AND casually in a sentence, can be confusing with the actual logical AND. So for the query U or X, we look at row U and at row X and perform a bitwise logical OR on these two rows, getting this, right? So U and X gives us 3, 5, 6, 7, 8, and 10. I haven't said it explicitly, but documents have IDs, right? I'll repeat that. So this is why we just say, but in fact, you could think of it as the title of a book as well, right? It's just some identifier for the documents that we use. Okay. Have another for you. Can you find a query that returns documents 5 and 8? So I give you 4 queries. There's U and Y, U or not Y, U and Y, and U and not Y. I want 5 and 8 as the results. $45. All right, let's start looking at the answers. Okay, wow, we have unanimity. And indeed, U and Y, you can see, if you do a logical AND bitwise of U and Y, you will see that only column 5 and 8 have a 1 in both rows. What that tells us is that document 5 contains U and contains Y, and document 8 contains U and contains Y. How many times? I absolutely have no idea. In what order? I absolutely have no idea. All I know is document 5 and 8 contain both U and Y. Okay? Who finds it easy? It's easy, right? Who is totally comfortable today? Okay, very good. Don't worry, it will get more complex. We'll get then linear algebra, super complex probability formulas in a few weeks. So we're just starting smooth, right? Okay. All right. In general, I recommend that you do not overestimate the power of simplicity. Simplicity is extremely powerful, the ability to describe things like that. In fact, the fact that it is simple with documents and terms and inclusion allows you to think one level higher, right, on what is a model, how do you model things. And I like to tell as a historical perspective how group theory and fields and so on actually came into life with Évariste Galois. Who heard of Évariste Galois? Okay. Many of you, right? He wasn't taken seriously back then, because what he was essentially doing is, taking addition, multiplication. Primary school kids do that, right? So he was taking addition and multiplication and saying, yes, plus we can abstract it away, right? So 2 plus 2 seems very easy, but if you abstract it away, 2 is a member of some set, and plus is an operation on 2 sets that takes 2 elements and returns another one. And then he started reasoning on an abstract level. So, okay, can you swap the 2, commutativity? Can you move around the parentheses, associativity? Do you have an element that doesn't change the result, like 0? It's a neutral element. Can you have absorbing elements? Plus no, but multiplication, yes, because 0 times anything is 0. And he wasn't taken seriously because I really thought, like, this is primary school math. What are you even doing? Except that this was probably one of the biggest revolutions ever in mathematics, because then came you know, the notion of ring, field, linear algebra that is now behind quantum physics, machine learning, and so on. Everything is coming from this super simple work, right? So never underestimate simplicity. It can really go a very long way. So the one thing that I want you to remember is not so much just that we have documents and terms, and documents can be included in terms. I want you to think one level higher. What is a data model? A data model has primary citizens, documents, terms, and so on, and it puts them in relationship with each other via inclusion, occurrence, order. This is a data model. We do the same with relational databases. We have rows, we have records, we have columns, and we basically define relationships between them. In fact, I remember, I mean, if you think very axiomatically in mathematics, in a math magazine, when I was a kid, that what they were doing is taking geometry, so the notion of line, point, circle, and so on, and replacing the words point, line, circle with different words, like carrot, rabbit, and so on, right? And basically say a carrot is on a rabbit, and so on, right? Doesn't make any sense, but actually axiomatically it totally does make sense, because you can define a whole axiomatic systems with rules and proofs and define things. And that will culminate with Gödel's theorem, right? With the notion of completeness and soundness, right? So this is when I tell you a term is included in a document, just don't stay at that level, but think one level higher in terms of abstraction of what it is that we are doing here. Okay, so this is a data model. All right. So as you can imagine, the incidence matrix is not the final way to go. There are more efficient ways that I will come back possibly after the break. I would like to anticipate on a lecture that will be in a few weeks on the evaluation of retrieval, of information retrieval systems. How do you evaluate whether a system is good or not based on what it outputs? So I'm anticipating on that, introducing just 2 concepts, and then we'll extend it in the week where we do evaluation. But in order to understand what's going on, I would like to come back to the concept of information need. An information need, as I said, is whatever happens in your brain. If you're lucky, you even have the English formulation. In some cases, you might not even have the English formulation. You just had a vague feeling for what you're looking for. But let's imagine that Alice right here has an idea of what she's looking for, and she's looking for the impact of global warming on the development of butterfly ecosystems in the southern part of the canton of Uri between 2011 and 2013, probably for her PhD thesis. So what is she going to type in the system? Because obviously that's, well, nowadays you can type that in a search engine, of course, but what about our Boolean query language, right? If we want to do it that way. Well, you could think of several ways, right? You could say, okay, butterfly and climate and Uri and south. You go to the library and type that in the query system. Or maybe Lepidoptera for butterfly and UR, which is the symbol of the canton of Uri and not winter. Or go more complex and say, okay, central, because Uri is in the center of Switzerland. Remember a beautiful ad of the SBB with dinosaurs. Anyway, central near Switzerland or Sweden, you never know, some people might confuse, and not Luzern or Nidwalden, Obwalden or Stockholm, and warmth, okay? So what I'm saying here is an information need might correspond to different queries. This is very important to understand, because if you only look at the queries, the system we have with our incidence matrix and the query system is exact. You have a query, and mathematically, the query returns or does not return a document. This is exact. So this system is perfect, right? If you just look at the queries, it's mathematically perfect. However, if instead of looking at the query, you look at the information need compared to the results, then it might not be perfect, right? Because the query might not be accurate enough to describe the information need. And maybe sometimes the query will maybe return something, for example, Sweden, in that case. Then you get a document. That document is relevant to the query, of course, because this is math, right? So the document is obviously returned by the query, but it's actually not relevant to Alice because she wasn't looking for Sweden. She was looking for Switzerland, right? Who understands that, right? So the query is perfect, perfectly mapped to documents, but the information need is not. And it is this imperfection that we want to evaluate, right? To say how good your system is, right? So let's take a break because I see that it's 11. And right after the break, I'll show you some evaluation metric, same as machine learning, really. All right, so see you after the break, I think probably at 16 past 11. Thank you.